So then let's directly move to the first talk. So the first talk in this morning is from Xiaolong Wang. Xiaolong is an assistant professor at UC San Diego in the ECE department. Xiaolong was a postdoc fellow at UC Berkeley with Alex Frost and Trevor Dario. He received his PhD in robotics from CVinW under the supervision of Abhinav Kuputa. His research interests include computer vision, machine learning, and robotics. Now let's give the time to Xiaolong to talk about his research in computer vision in robotics. Xiaolong, please.
Okay. You can hear me, right?
Yeah.
Okay. Thank you for the introduction. So thank you for inviting me for the talking here. Today I'm going to talk about our work on perception in the wild, especially in the angle of how we think about it when we try to apply it in robotics. So let's take a look at this video first. So both the baby and the dog observe and act in a dynamic environment. So the baby observes the ball and takes it to the dog, and the dog observes what the baby does and responds back. To understand and act with our visual work, we need to understand the geometry of the object and how the object moves dynamically. And sometimes understand the semantics is also very helpful because we know that the ball is safe for the baby to play. So can we use this kind of knowledge of 3D and semantics to help the robot to learn? So in the past few years, there are lots of advances in robot learning. So you can see some pictures in here, but all these works are still quite limited in the lab setting. And then if you look at these pictures on how we actually want the robot to work in this kind of kitchen, you will see there's a large contrast between these two kind of setups. So the key to deal with the real world problem for perception, I think, is to learn rich and generalizable visual representations. So how to learn a good visual semantic representation? A lot of vision work has made a lot of progress in different classification and detection tasks. But fundamentally, learning all these tasks in a supervised setting, basically, you can only use limited data, and also a more serious problem is that we can only perform classification or recognition with a limited database or categories. So I can actually hear some noise in the background. Maybe I can, or someone can mute someone. So besides the limitations of the semantic labels, the 3D labels are actually also very hard to obtain. So in a lot of 3D interaction work that we try to learn how hand manipulate objects, we are actually collecting the data in the lab environment or wearing some motion capture systems. So this really limits us to understand the 3D interactions between human and object. So in this work, so I'm basically trying to introduce two lines of our research that we try to generalize the perception to learn semantics, but not limited by categories, to learn the 3D structure and the 3D geometry and shape of an object, but not in a constrained environment, but actually an environment in the wild. And by enabling this kind of learning, we applied we can show some demos that apply to our robotic systems, including some leg robots and also manipulation with the dexterous hand. I'm not going to talk about a lot of these things, but mainly actually focus on the vision side today. So the first work I would like to introduce is actually a CVPR work, and then following some extensions on this GroupViT. So this work essentially is actually offering a pre-trained network. So it's actually a work, you can think of it like CLIP, but then we are basically trying to train the image text large scale model that can directly zero shock transfer to semantic segmentation, but not just doing image classification. So for example, in here, we propose a framework that first learns to group regions, to group pixels into regions inside the VIT, and then do classification on the regions to get segmentations. So all these learnings of the framework actually does not require any pixel labels or any structural labels or bounding box labels. All we need to learn from is just large scale image text pairs. So we have basically learned on 400 million image text pairs. And we design the architecture, which is called GroupViT, which takes the image in as input and then performs some grouping mechanism inside the vision transformer in a hierarchical manner. And then finally, we get the groups, and these groups will be doing contrastive learning between the text from the intellects. So by learning in this way, eventually we can actually, given any image in test time, we can first perform grouping and then do basically labeling the group by query the text with any given dictionary. So essentially we can do in the open set setting. So again, as a quick summary, it's basically will be something look like a clip model, but then it is we're adding a grouping mechanism into the VIT, and that allows it to actually do open set semantic segmentation. So here I just want to briefly go through the Legwort kind of architecture. So essentially, it's following a very standard vision transformer Legwort, but the only thing different is that we actually add additional learnable group tokens. So these are some learnable parameters. Essentially, you can see them as some like clustering centers, for example. So the grouping block in here we design is essentially a attention mechanism that try to basically group the input token regions into different groups and according to this clustering center. But assigning these input patches into different segments, so we can get different groups as the output. And then following up, we basically perform transformer blocks on top of these grouping, on top of these group regions instead of these regular patches. And then we can also further perform grouping basically from smaller groups to larger groups and then going to the end. So essentially, we are doing some bottom-up grouping as the transformer is going forward, and it's not performing like sliding window kinds of or convolution kinds of operation. It's basically depending on the shape of the objects, we can group patches into different regions. So the final loss is actually very simple. Essentially, we have all the group regions feature. We just average them. By average them and then doing contrastive learning between the image level, by average them the segment features, we can get the image level feature. And then we do the contrasting learning between text and the image level feature. So somehow, interestingly, by doing so, it actually encourage the grouping automatically happen inside the Legwort. And then we can actually in test time find correspondence between a particular group and a particular text and do basically do similarity matching for labeling. But all the training part is happening in the average pooling feature. So I find this is particularly interesting. And if you want to think about how this happened, I mean, you can kind of relate to a model like CAM or GradCAM. So essentially, people have tried to train image classification, but then they find out that they can actually use the classifier to activate the regions that give you the segments of the object. And then here is basically very similar, right? So you just do contrastive learning for the whole image, but then you can actually use the text to activate to see which regions it has the most high response. We just provide the mechanism of grouping inside the Legwort to allow these regions to emerge. And that is essentially the center idea of the GroupViT. Everything else is just very standard contrasted image text contrastive learning. So we do some visualization on the group tokens, and we essentially show that there are some emergence of ideas of the semantics in different layers of groups. Some groups look at the limbs of the object or the animals and the humans. Some groups basically look into the background, like the grass. So essentially, it is showing that the group actually learns some concepts and help us to do clustering on the image tokens. So this model transfer pretty well to, in zero-shot setting to many classification tasks. So we can see some results on Pascal VLC that we first do grouping and then do labeling on it using a Pascal VLC dictionary. And then so changing a data set is the same. We don't need any fine tuning, but just use this large scale pre-trained network to do this kinds of object discovery and then labeling using the text encoder. We also like provide a demo in the hacking phase space. Essentially, you can upload a picture and then upload a dictionary or the word. For example, in here, on the top right and the bottom right, we can segment the robot out, and then you can also label the robot with this robot class. And then this is a baby girl. So you can segment the baby girl out and then label it with baby girl. And then this is also a cartoon character. You can segment the character out and then label it with the Luffy, the character. So using our network.
And
so
Xiaolong, a very quick question. So what's the
right.
Difference between the semantic map visualization and the groups visualization?
Right. So the groups actually, there's not that many groups. Oh, you mean the visualization here? So the group in here on the bottom is basically there's no, it's just the grouping region output. And then the semantic map, basically you use some categories, right? And then you compute dot product between the category embeddings and the group embeddings. And then you basically select the most similar response as the classification results, and then you set a threshold to basically get the segmentation as the output. So it's just essentially a labeling process. The segment is the same. It's just some segments are labeled as background, so it's not show. Some segments is labeled as the dictionary we provided. So that is the difference. Yeah. Okay.
Yeah, thanks. Please,
yeah. So if you have any question, please go ahead. So this work is quite exciting to us, but then there's also a thing that I'm not very happy with is that essentially the resolution is pretty low, right? So you just have eventually a few groups, and then these groups are basically constructed by the visual tokens, and then you have all these square things there. So it's not a very high resolution segmentation work. So recently we basically kind of try to extend the use of the grouping mechanism, not necessarily in this like large scale pre-training kind of image text learning, but just apply it as an architecture improvement. We specifically look into this kind of non-hierarchical vision transformer. So personally, I would like to call it like a network with pyramids or not pyramids, right? So somehow hierarchical is some words that from some old papers, and then people kind of iterate on this non-hierarchical or hierarchical. So essentially the hierarchical one is something like swim transformer. You have high resolution, lower resolutions, and then you have more like a conflict going up. Along hierarchical is more like just the plain VIT does not have any like keeping the same resolution all the time. So there's also what like this work that from Meta also presenting in this ECCV, showing that training plain vision transformer has some benefits and simplified the learning, kinds of making pre-training and downstream fine-tuning easier to connect. And then also, ideally, you don't need to use many levels of features. You can just use the final level of features, and then that makes everything much more simpler and clean to do this kind of hierarchical VIT. But then, of course, by doing this work, this kind of work, there's a big issue. Basically, if you want to increase the resolution of your input patches, right? So you double the number of tokens or triple it. So then your complexity of the self-attention directly increase by square. So that makes the memory very unbearable. So how do we actually still train this kind of plain vision transformers without using such a large memory? So the answer we provided here is also similar. It's basically inspired by the grouping mechanism. So essentially, giving a large high resolution features, many tokens, you can actually first do grouping on them. So the feature grouping part is the same as what we did in the GroupViT. And then instead of doing self-attention across different image tokens, we can actually do attention between different groups, right? So it's basically propagating information among different groups. So we call this like group propagation. So information is only happening, propagation happening among different groups. So once the group regions are updated, we basically do some ungrouping to copy paste the information back to the original image tokens. So that's how we kind of doing this kind of propagation using this grouping mechanism. And because it's always can copy the information back to the original image tokens, so we can actually insert the block in any layer of the legwork and then make it a more plain transformer, meaning that every layer has the same resolution, and then we can do very high resolution inputs and high resolution outputs in this way. So just to give you some visualizations, we basically show that for different applications, we basically show some grouping results. Here, basically the same color represents the same group. It's not as clean as the previous GroupViT thing because it's in the intermediate features. But then we basically show that we are only going to do self-attention between the groups, not inside the groups. So that makes the computation easier. So we compare to some baseline, like for example, some swim transformer legwork, which is a relatively old baseline, but we still show improvement, like similar parameters. We can actually improve 4 to 5% in instance segmentation, object detection. But this is more like a standard, like image net pre-training and fine-tune on COCO settings. And then in some segmentation kind of 80-20K thing, we have half-size the parameters, but then still show like 2-3% improvement over swim transformer and some other approach. So it's not that much, but then essentially we show that we enable the plane transformer to work much better. So hopefully this can inspire some future work that allows some more studies in here as a parallel work as this hierarchical transformer board. Okay, so this is basically some work we did in the segmentation and recognition side. Of course, in the core of the robotics problem, there's also 3D. So the robot needs to understand the 3D to operate in our physical world. So in the following work I want to talk about is some recent work we did that we tried to do 60 object pose estimation in the wild data, and then do it in a self-supervised manner, meaning we don't use any 3D labels to do this kinds of 60 pose estimation. So 3D bounding boxes and 3D like rotation. So I was first introduced a little bit about the data set we collected actually. So you will be surprised that there's not actually many RGBD video data sets in the wild. All the robotics people are working on YCB data set. Essentially, there's like 20-ish instance, and then that's it. Basically, there's no categories and whatever. So I find it is really worrying. So we did some efforts on actually collecting more diverse object data set. So you have RGBD, not just RGB. And then it is sticking over many different places. So here are some examples of the data we collected. We just use the iPhone to go around the objects. So we have now 5,000 RGBD videos for around 1,700 objects. Believe it or not, is already a lot. So we did basically, we don't provide a lot of annotations for here because we don't have much money. And then we only provide the 3D annotations for the test set in here. Okay, so for this work, we basically try to, and I think the 5,000 videos only spends like $5,000. So in the future, we think we can scale better. So in this work, we basically use this data set and then try to see whether we can actually do all this post estimation in a self-supervised manner, not like using human labels, because we don't have the money to get the labels. So given this data set, so the key for the 60 post estimation is actually finding the correspondence between 2D and 3D. So once you have the correspondence, it's very easy to get the boxes out. So essentially, the idea is basically the central thing we need to solve is basically given this pixel image and the 3D shape, we need to find the correspondence between the pixels and the vertices in the 3D shape or mesh, and this kind of UV map kind of thing is basically showing the correspondence, right? And then on the other side, 3D to 2D correspondence is something can be used to help us to do the learning as well. So we put this kind of learning in some differentiable rendering kind of framework, like reconstruction and rendering back to 2D. I mean, it's a pretty standard kind of technique to apply on this kind of framework. But of course, this kind of learning alone does not really work because there's a large shape variety. I mean, I show the bottle in here. It's not that large shape variety, but in general, there are a lot of other objects that in the data set that has a large shape variety makes the learning very hard. Oh, by the way, it's all training on category levels. So essentially one model for one categories. And then we assume there's a canonical shape that's like roughly looks like a bottle, which is also learned for one model. So given basically the inference is very simple. Once we find the 2D to 3D correspondence map, we can do some post fitting to get the 6D post as the output. So again, the center and most important thing in here is basically try to find the 2D to 3D correspondence in an automatic self-supervised way. So one thing, one loss we apply basically in here is essentially like a single instance cycle. So essentially, given any pixels in the image and given the mesh shape in the 3D space, you can find the correspondence between 2D and 3D, and then find the correspondence from 3D to 2D, and then you should go back to the original locations. So completing a cycle helps us to find the correspondence. And similarly, on the right, it's the same. You can go from 3D to 2D and then 2D back to 3D. So there are two cycles in here that we can use to learn this correspondence. And this technique is also kind of introduced. It's not new. It's introduced in the CSM paper, canonical surface mapping paper, proposed by Nilesh, Shubham, and Abhinav. So what we do is new in here. I think is particularly interesting is that given like nowadays we have this very powerful like self-supervised pre-trained like 2D model. So specifically we use Dino in here. We can actually get very, very strong like 2D correspondence given this self-supervised pre-trained model. So what we're doing here is creating a 4-step cycle. So what you do is you can get assuming you have the 2D to 3D cycle, and then between the two 3D shape, because it's deformed from the same canonical match, so automatically the vertices themselves has the correspondence. So this is basically an identity thing. You don't need to learn about it. And then you have this 3D to 2D cycle back, go to the 2D image, and then to complete the cycle, right? So we use basically the Dino features to find the correspondence. It's a pre-trained Dino network. And we find it actually is quite useful and quite robust. And given this 2D correspondence guided learning, by completing these 4-step cycles, we can learn very robust 2D to 3D correspondences. And this is the key that actually make this framework works. I mean, there's a lot of losses when you are doing with 3D reconstructions and post estimation, but around all the losses in here we try, we find this is particularly useful thanks to the large scale pre-trained 2D models. So essentially here are some results that we basically show that we can get like different bottles and then learn the correspondence, get the 60 shapes, and this is all performing in the unseen data set. I mean, so in robotics, actually, if you don't know, it's usually trained on text on the same instance, but then we basically show that we can do it in the wild and actually test on test instance, and then it still works pretty well in a self-supervised manner. So we report some numbers, and this is a relatively new data set. So if you use supervised learning, there are some old data set that have limited data. It doesn't really generalize well to this new data set. And then we have the semi-supervised learning approach before, which is leveraging simulation data and this wild 6D data without labels. And we find that our self-supervised model can perform almost as well as the semi-supervised approach, giving these benefits from the dino feature. We find these results is basically quite exciting here. Okay, so that's basically this 3D work that we are recently very excited about. So when we have done all this vision work, how do we? So in my mind, is basically it should always to be applied to something, right? So in our lab, we basically worked on different robotics problem, including locomotion control with visual guidance, and then also dexterous manipulations that's using the 3D object pose, right? So on the left side, you can see clearly we can apply something we produced from GroupViT and beautiful semantic segmentations to guide the robot to how to walk in the Y environment. And then grasping the object also requires the 3D estimation. I will spend maybe like at most 1 minute to introduce some of this work. So this is a work that we performed this kinds of locomotion control, actually using the front head cameras in the robot, and then it can learn to walk and avoid obstacles. So the vision input right now can be incorporating with 3D understanding and also this kinds of segmentation network to help like walking better. So there's a lot of work that we presented in ECCV. Actually, this is our old work, but then it takes a long time to get in. And you finally get into ECCV. It's basically, we try to learn dexterous manipulation from human videos. So because in the wild, because it's done 1 or 2 years ago, so vision in the wild still not work as well. So we have to end up basically collecting data in our very, in the lab setting that's basically try to collect in this green background kind of table, unfortunately. So essentially we collected the video data and we estimate we detect the objects and estimate the pose, and then do retargeting, essentially give you basically the robot demonstrations how to manipulate objects. And then you can basically learn a policy on top doing imitation learning. So I hope that like with the new techniques on pose estimations and the vision in the wild techniques, we can actually use more in the wild data, not this like green table. But here is an example showing that why imitation learning is actually important. So essentially, you can see learn from reinforcement learning on the left and imitation learning on the right. If you can behave more like a human, it actually makes sim-to-real much better. Essentially, it will act like a human, makes the transfer to sim-to-real much better. For example, in here, if you flip a cup, if you just learn from RL, you just try to find some random way to flip the cup. But if you learn like what a human do, you can actually put the finger into the cup and then flip it. So that is helping much better on sim-to-real transfer. So that is the overall. I mean, there's a big graph in here showing what our lab is doing. It's a little bit scary, so I didn't put it in the beginning. But essentially, I introduced the first row of it. So I need to. So I'm still very much onto doing like training vision foundation models, and then I would like to connect this to robot learning and eventually deploy them to the real robots. So we're working on multiple different robots, and then I think from going on, we can use this real robot application to driven back to the vision foundation model learning and see what we actually needed to solve the in vision to solve the robotics problem. So I think that's all for my talk today. So I think I still have around 2 minutes. So if you have any questions, please, yeah, go ahead.
Yeah, in fact, we have 3 minutes for question answer. So anyone in the group have questions? While people are articulate their kind of question, in fact, I have very nice talk. So I have several questions to ask. So first, Xiaolong, you mentioned several times about kind of dino or kind of definitely right. in later, but in fact, in your first GroupViT work, about unsupervised
Right.
segmentation.
Right.
You are doing it in clip way, but Dino also do it in a self-supervised
Right.
way.
Yes.
Dino also show very
Yes.
good semantics. It's not semantic segmentation, but it's just like unsupervised segmentation result. So how do you think that's kind of your GroupViT work, the groups funded by your work is similar to the groups funded by Dino, or in fact, what's the connection between them?
Right. Yeah, that's a very good question. We actually did. I don't know whether we compare it in the paper. We definitely did compare in our own debugging. The way that Dino, in my personal opinion, to report the segmentation is a little bit strange because they are more like they have different heads of attention, and then you from different head you can different background segmentation, and then you select the most similar one comparing to the ground truth, and then that is your results. So it's kind of a little bit cheating to me, like you know the ground truth and then select the best one and then compute the number. But yeah, but maybe that's the only way to evaluate when you are unsupervised segmentation. And I think, yeah, it's particularly relevant. So if we don't consider the labels, I think it's pretty relevant. So I think the difference is basically the learning part in here, we actually is more like a language driven. So we are actually able to find regions that like more semantically meaningful, I would say, because by evaluating the same way as Dino evaluation, we actually get much better results on the regions. We didn't report it because we feel like the right way to do things is to not using ground truth to compute the inference process. But yeah, so we did actually have the experiments when we are debugging, and I think but the limitation, of course, is like in GroupViT we are grouping the regions more and more smaller and smaller, like smaller resolution in the end, because we only like have 8. You can see it has 8 region tokens as the outputs. But Dino actually, I think eventually still have the same resolution as the outputs, so you can use as high resolution pre-train to do a lot of stuff. So I think in our way it's more like hierarchical grouping up, and then this lower resolution going to the end. So that is the disadvantage from ours. Yeah, but basically that's how I see the comparison between two. Yes.